Black holes are a bizarre and fascinating feature of our universe. They form when gravity bends a massive amount of extremely dense matter into a small space, creating so much gravitational pull that even light cannot escape. It's a natural occurrence that can be triggered by a dying star. But until now we have not deeply investigated or studied black holes. The big reason you can say is the lack of advanced tech, but as of now, we have James Webb Telescope that is way more powerful than any other telescope. Physicists come to know that black holes display some of the weird and wonderful behaviors of quantum physics. One such behavior is superposition, where particles on a quantum scale can exist in multiple states at the same time. You can simply understand it by the example of Schrödinger's cat, which can be both dead and alive simultaneously. Take a pause and imagine a situation where you are alive or dead at the same time. It's fascinating. In the study of black holes, we wanted to see whether they could have wildly different masses at the same time, and for a surprise, it turns out they do. Imagine you're both broad and tall, as well as short and skinny at the same time. For a normal person, it sounds like a naturally puzzling situation. This is because our knowledge is rooted in the world of traditional physics. This situation can be bizarre here, but this is reality for quantum black holes. The microscopic structure of black holes is poorly understood, and if studied deeply, it could open a window to solving cosmic mysteries. The universe is showing us that it is always stranger, more mysterious, and more fascinating than most of us could have imagined. Most of these massive objects float through space invisibly, making it difficult to answer the many unanswered questions about their mind-bending properties. Scientists have proposed that searching for specific signatures in space could help them confirm a key mystery about black holes: whether they produce vortex structures. These vortexes would be structurally similar to tornadoes and whirlpools, but they would form in multiple locations on black holes instead. According to a recent study published in Physical Review Letters, these clues could potentially open an observational window to various hidden sectors of the universe, including the nature of dark matter. While popular depictions of black holes often depict them as massive space vortexes, the presence of turbulence in these entities is debatable. Researchers at the Max Planck Institute for Physics in Germany, led by Jihad Valley, have presented new theoretical evidence that rapidly spinning black holes naturally support a vortex structure, and that black hole vortexes can also have macroscopically observable consequences. Scientists believe that understanding the vorticity property of black holes can be achieved without digging deeper into the complexities of quantum gravitational computations. The new study was inspired by experimental studies of Bose-Einstein condensates, suggesting that black holes are made of gravitons, which are the hypothetical quanta of spacetime itself. It has been demonstrated that their fast rotation produces the appearance of vortex structures. Based on the experimental data, the researchers confirmed the presence of black hole vorticity in theoretical models. The findings have numerous implications, including explaining why rapidly rotating black holes do not appear to produce Hawking radiation. The boundary of a black hole produces hypothetical particles known as Hawking radiation. This radiation suggests that the temperatures of black holes are inversely proportional to their mass. To put it another way, a black hole should glow hotter as it becomes smaller. Although it has never been observed directly, Hawking radiation is a prediction supported by combined general relativity and quantum mechanics models. It is named after eminent physicist Stephen Hawking, who made the argument for the existence of black holes in a paper titled Black Hole Explosions in 1974. The structures could also lead to extraordinary breakthroughs beyond black holes, including the opportunity to open a portal into the sector of dark matter. Dark matter is a mysterious substance that does not fit into the standard model that currently explains our universe. According to Michael Zantadeschi, a PhD researcher at the Max Planck Institute of Physics, dark matter could be made of particles with extremely small electric charges several orders of magnitude smaller than an electron. As we show, such particles interacting with the black hole vortex would result in the extremely powerful electromagnetic emission from the black hole, which could be detected. This is a path we surely plan to explore in depth in the future. Black hole vorticity and all of its consequences may be revealed by studying extremely luminous objects known as active galactic nuclei, which are fueled by supermassive black holes that reside in the centers of giant galaxies. These nuclei release enormous plasma jets that can span 1,000,000 light-years and accelerate to almost the speed of light. These powerful jets may emit magnetic traces of vorticity in their light, which would be visible in telescopic photos. Dark matter is also believed to interact with the jets. Future investigations of jets and their potential vortex signatures could, therefore, among many other uses, contribute to the enormous scientific effort to understand dark matter. Scientists are currently investigating the generation of magnetic fields from vortical black holes. It appears that vortices can explain the strongest magnetic fields in active galactic nuclei. Moreover, vortices in so-called primordial black holes, or black holes formed in the early universe, could account for the magnetic seeds required for the observed galactic magnetic fields, resolving both this and the origin of dark matter. Black holes hold information more than we can ever imagine.